Hello everybody, these are the video notes for Chapter 2, Section 1. Essential questions for this section: how are distance and displacement different? How is an object's speed calculated? And what information does a distance time graph provide? There is old vocab and new vocab we need for this section, and there are two of the definitions. The third one will be coming up later. Distance is basically how far something goes, but displacement is how far it goes from a reference point, from a starting point. So if displacements are in the same direction, they can be added. 5 meters east and 5 meters east is 10 meters east. If they're in the opposite direction, they could be subtracted. 10 meters east and 5 meters west gives a displacement of 5 meters east. And displacements that are not in the same direction or in opposite directions cannot be directly added or subtracted. So here we have to use the Pythagorean theorem, because if we go 4 meters east and 3 meters north, our displacement is 5 meters north. Two things I want to show you in relation to this. First is a movie clip that kind of pulls this together.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Do you want a demonstration? Oh! Ah! Shoot! It's so difficult sometimes to get the piranha back inside.
So Vector says that he is an arrow that signifies both direction and magnitude. Well, I figured probably the best thing to do to show you that was to pull up another PowerPoint that I found that I really like. And in this PowerPoint, it shows this. Scalar. First, it kind of gives just a general overview of many things we're going to bring up later this year. Scalar quantities versus vector quantities. Scalar quantities are magnitude only. An example, the speed of the car was 60 kilometers per hour. That's a magnitude, a number and a unit. Vector quantities are magnitude and direction. So 30 kilometers is a magnitude, a number and a unit, but this also has direction. That makes it a vector. Well, we draw a vector by, like Vector said, it's an arrow. The length of the arrow represents the size. The direction indicates the direction. So something may have this weird path in blue, but the vector is a straight line that goes from one end to the other. Well, distance is scalar. Displacement is a vector. If we have a bear that goes 7 meters to the tree, back, and then to the house, the distance he would have gone is 26 meters. 7, 14, plus 12, 26. But the displacement the bear would have would be 12 meters in an easterly direction, because he's simply going to the house. Doesn't matter that he went to the tree and went back. From his starting point to his ending point, he went 12 meters. So, in order to show this in yet another way, I am going to draw a dot, and we'll say, well, maybe I'll draw a dot. I'm going to draw a dot right there in red. I'm then going to move this arrow so that it's on that, it starts on the red dot. Well, now I'm going to move this arrow so its tail is on the head of the first arrow. And then I'm going to move this arrow so its tail is on the head of that arrow. And then I'm going to use green. Then I'm going to draw a green arrow, a green dot right here to show where we ended. And then I'm going to draw a dashed line to show that this is where we went from to where we finished. Now, I'm not perfect because I'm going kind of fast, but you can see that all of these arrows, all of these would be the distance, but this is the displacement. So now what I'm going to do to kind of show you all this is we're going to do them in a different order. Let's do this arrow first, and then let's move this arrow over here. Notice I keep putting them nose to tail, but notice even if I do them in a different order, we end up in the exact same place. So now let's try this one, and then let's do this one, and then this one, and same thing. It does not matter how we put these arrows. If we go nose to tail, they will always end up in the exact same place. Red will always start here, green will always end here, and it always goes in the exact same direction. Now what I would like to do is talk about speed. Speed is the distance an object travels per unit of time. Any change over time is called a rate. Anything we measure that we divide by time is called a rate. So if you think of distance as a change of position, then speed is the rate at which distance is traveled, or the rate of change in position. So if we take this equation, speed equals distance divided by time, and we simply rewrite it, and we multiply both sides by time, time cancels, distance equals speed times time. Well, any equation that we can write like this, I would like you to start to try to think of it like this. I'm going to take distance because that's by itself, and I'm going to give it half of this circle, and since these two are on the other side, I'm going to put speed and time here. Why the reason I'm doing that is because of what it now does. If I cover up speed, look what's left, distance divided by time. If I cover up speed, because that's what I want to solve for, now I get distance divided by speed. And if I cover up distance, because that's what I want to figure out, how do I mathematically do it? Speed times time. If we do an equation in this format and rewrite it like that, covering up what we want to solve for mathematically shows us what we need to do. Speed, distance divided by time. Time, distance divided by speed. Distance, speed, times time. So keep that in mind as we go to the next slide. A car traveling at a constant speed covers a distance of 750 meters in 25 seconds. What is the car's speed? So if we do what I just showed and we take distance and take speed and time, because speed is distance divided by time, distance is speed times time, but what do we want to know? We want to know the car's speed. We know the distance, we know the time. So I want to know the car's speed. We need to take distance divided by time. So speed equals distance divided by time. I know that's the same thing that the previous slide showed, but I would just want to show this to you because whatever I give you, I could give you any of these three. any of these two, you ought to be able to figure out the third one. So if we take distance, 750 meters, divided by 25 seconds, how about seconds? We then get 30 meters per second. Okay, it all works, and let's now work through it in the PowerPoint. That's what we knew, that's what we're trying to figure out. We set it up, we solve it, and that's approximately what the speed limit in the United States interstate system is. That's about 70 miles per hour, so that is a reasonable answer. In order to show you a distance and time graph, what this is going to show you is if you think about what the slope shows, and we should know how to do slope, it's rise over run. So if you figured out the slope of this line, the slope of this line, the slope of this line in 3 different places, because the slope changes, what slope does is it tells us speed. Why? Because it's rise over run. Rise in meters over run in seconds is meters per second. The math works out perfectly that the slope of a distance time graph tells us the speed. But speed is not always constant. How does the slope of the graph change when you speed up or slow down? What happens to the graph when you travel at a constant speed or stop? This is not a distance versus time graph, this is a speed versus time graph. And notice how the speed is changing. You're gaining speed, you are slowing down, you're going down a hill, you're stopping for a red light, you speed up, you're going a constant speed, you slow down. Average speed describes the speed of motion when speed is changing. So if speed is changing, it might be going up and down like it was on this graph, but what's the average? The average is the total distance divided by the total time. This person is going all sorts of speeds, but if you take how far they went and divided by how long it took them, you'll get an average speed. Graphing motion, the motion of an object over time could be shown on this distance time graph. The fastest car here is the red car because it has the highest slope. If you took and figured out the slope of this red car, but also because it's angled the most, that's the fastest car. Then we got the blue car. The green car is a little crazy because it has a slope, then it has no slope. This car is not moving, and we know that because the distance is not changing. It is staying at 2 meters, and it stays there for 4 seconds. It's not moving, but then it starts moving again. So the fastest car is the red car. The second fastest car is the blue car. The green car is actually a couple of them. It's got a slowest slope here, but here it's stopped, but here the green car is going as fast as the red car. So on average the green car goes the slowest, but from 8 to 10 seconds it goes as fast as the fastest car. So here we have Mary, Kathy, and Julie. Much like the red, blue, and green car earlier, Mary's going the fastest. And now we actually figure out the slope. It's 80 meters per minute. Now Kathy is 60 meters per minute. But look at Julie. Julie is 40 meters per minute for a while. Then she stops. Then she keeps up pace with Mary and goes as fast as she does. And look at the slope. They are the same. The graph shows the line representing the motion of the faster swimmer is steeper. The object's speed is equal to the slope of the line on a distance time graph. So there are our essential questions in vocab again. To finish this up, I would like to show you 2 things. First is a video on the website for our book, and here we go.
A graph gives us another way to describe an event. This graph of distance versus time tells the story of a girl named Chris and her dog during an 8-minute walk. As Chris and her dog move farther from home, the graph line moves upward. When they stop, their distance from home is not changing. The graph line moves upward again as Chris and her dog start walking again. The graph becomes horizontal, telling us that they have stopped again. Chris and her dog have now turned toward home. The steepness of the graph tells us that they are moving faster, probably running. At the end of the walk, 8 minutes have passed, and the distance from home is again 0.
Two problems I have with this PowerPoint or this video. First is the fact that they call it distance. Well, that's fine if it's always going up. With our cars and our swimmers I just showed you, they're always moving away from their starting point, and distance is fine to use if they're always moving away. But if we keep saying distance from home like they do in this video, they really ought to call this displacement. The other thing is, the girl and the dog are always moving to the right, but then they say that they are moving back home. Notice this is a negative slope. That means that they are going the other way. Instead of moving to the right, the dog and the girl should be turning around and moving to the left.